Hello there, and welcome to this tutorial on how to use the auto model function within R. What we're going to be doing here is doing a brief run of the auto model function on a dataset about the Titanic, and then going through the console output and providing some brief commentary on what's happening at each stage in the process. So, brief introduction. The auto model function is a function which is designed to automate the analysis process. I should make note it's not designed to be a be-all and end-all of the analysis of a dataset, and it should be seen more so as a kind of initial preliminary analysis. So alongside the same time you would run a summary if you know R. Excuse me. Alongside the same time you would do that. So it's getting some initial models made on your dataset with very little context, and you can then explore further depending on the results seen. So what we're doing first is, because this package is not on the CRAN network, we have to do a local install, which is done using DevTools. So we're just going to install it here. Maybe one day it'll be on CRAN network, so everyone can use it. But in its current state, it's definitely not ready. It's not polished enough to be a actual package on CRAN. Then once we've installed, we can load it in just like we would with any library. We go library auto model. It's now loaded in. What we're going to now do is read in our data set. So if we have just a brief look, we see we've got 12 variables. We've got like passenger ID, survived, class, name, sex, age. It's basically some just metadata around the passengers on the Titanic. And we're going to be interested in modeling / predicting this variable here, survived, where this is a binary variable telling us if a passenger survived the Titanic or not, where is 0 is that they didn't survive and a 1 is that they did. Cool. So now that we've got those brief initial steps out of the way, here's our run of the auto model function. Missed the L there, but here we go. So this is our auto model function call. This is the first variable it takes, which is the name of the column we want to predict. So in our case it is survived. And then we pass it the data set, which contains that variable and all the other variables we want to use to predict it. So we can hit run, and we see a lot of stuff has just come out in the console, which is fine. It took about 1 second to all process, but let's go through it. Okay, so here we are. So what's happened is AutoModel's taken that data set, it's done various cleaning and transformation techniques on it, then modeled it in 5 different ways. So it's modeled it using k-means, k-nearest neighbors, classification and regression tree model, so CART, ordinary linear regression, and elastic net regression. And we're going to go into those as we go through this output here. So firstly, we'll look at some of the cleaning and transformation stages. So firstly, it's detected there's 866 NA cells, or missing data values, in our dataset, which accounts for roughly about 8.1% of the data. After that, we're now doing a check on the data types within the dataset. So if there's a column which is string or non-numeric, it's going to find that and encode it in such a way where it is numeric and can be used for analysis. The algorithm works alphabetically, so you'll see that female will be encoded 1, male encoded 2, because F comes before M in the alphabet. And in this run, it's found 5 variables which need to be re-encoded. These are name, sex, ticket, cabin, and embarked. So it's gone ahead and recoded them as factors or numeric, so they have numerical values now. After that step, it's now doing a step where it's removing variables which have too much of their data as missing. The exact case is that if variables are removed since they had greater than or equal to NA% of their data missing, or as NA values. The default's 20%. So if a variable has 20% of their data missing or more, it's removed. In this analysis, it's found one variable which is such, and that is the variable cabin. So it's removed cabin and moved on from there. In the background, this is where some user customization can go on. So if we just here, after doing the load data removal, it performs a list-wise deletion on the rest of the NA values, so that you have a complete cases dataset. However, if a list-wise deletion isn't wanted and you believe that some missing value imputation can be done based on the dataset's assumptions, you can pass this variable to the function. So you'd say imp flag true, and what this is going to do is it's going to do a single value imputation, cart imputation I should say, on the missing values, so that then the NAs, instead of being list-wise deleted through list-wise deletion, they're imputed using classification and regression trees. But we won't run that just to keep the console clean, but it's there as a feature. Cool, so if we go back up here. Okay, after that, we're now looking at low-level removal within factors, which is close to can be considered as an outlier check for factor variables. So what this is doing is it's finding variables which have a low amount, it's finding levels in factor variables which have a low amount of observations. So what it's done here is it's found that level 4 in the variable parch should be removed since it only had 4 observations. And it's done the same for level 6 in parch should be removed because it has 1 observation. And the reason why we do this is because if we were to model our data on level 6 with only 1 observation, that doesn't provide a lot of predictive power, because we don't have a lot of data to work with to correctly represent that level. So the level at which the amount of observations needed, at this stage can be set using the function or variable levels. By default, it's set to 5, but you can change it to 10, change it to 15, change it down to 2, up to the user's discretion. But that provides a little bit of customization based on the results you see here. And as you see with this final row here, it says 2 total levels removed from 1 different variable, in total 5 observations deleted. Just a roundup of the section. Cool, so after that, we've then got the variance 0 checks. So what the variance 0 check is after removing those levels, it's now seeing if those variables if all the variables still hold variance. And what that means is checking if the variable isn't just the same value for each observation. The reason why we want to do that is because a variable which is the same value for each observation provides no predictive or modeling power, and keeping that variable in is just going to clog things up, add unnecessary variables that don't really do anything. So this step aims to remove them if they exist. In our run, it's found none at this stage, so it's said 0 variables removed. Cool. After that, we have dummitization of variables, which is where we're taking factor variables and we're encoding them as one-hot binary variables or dummy variables. So an example of this would be, if we were to open this up, let's have a variable called var a, and it takes the values 1, 2, and 3. when we're performing dummatization on this, or turning them into dummy variables, what we're doing is we're turning var_a into two new variables. So we'll do like this, where we've got var_a.2, which is 0 if the value of var_a is not 2, and then 1 if the value of var_a is 2. And then it will do the same for var_a.3, where if the value of var_a is not 3, it's a 0. And then if the value of var_a is 3, it's a 1. And then those variables will now be added to the data set and represent var_a as a whole. So we'll go from there, and it gives what it does here is it gives an output of how many new variables, or the variable count, how it's changed. So it's gone from 10 to 21 through that transformation. And then after that, after the dummatization, we do another variance zero check, because some factor levels, so it's more so an internal thing in R, some factor levels that cause the dummatization may not have any observations. And if you look, you can see it's removed parch.4 and parch.6, and that's because if we look in low level removal, we removed all those observations of those levels. So this is just a kind of backstop cleaning check, less so than a more theoretical mathematical step, if that makes sense. Doesn't really make sense to me, but oh well. So now onto our first model. The reason why we still have some cleaning steps to go, but the reason why we're doing our k-means model now is because the future cleaning steps that we're going to do negatively affect the k-means model. So it's better to do it before those. So what we've got here is our k-means model. We can set the amount of centroids we want. However, there's a if-else statement deciding on a kind of good automatic amount of clusters to be made based on the predictor variable you've given auto model. So in our case, survived has two levels, or two values. It can take either a 1 or a 0. So what k-means is identified is that, and it's decided to make two clusters for that reason. So it's made two clusters, and then we can have a look at the results of what observations are in each cluster using this table. So along the y side, or the vertical side of the table, this is the cluster number. So this is cluster 1, this is cluster 2. And then along the top, or the horizontal, is the value that our predictor or dependent variable, or the variable we want to predict, the value it's taken. So this is 0, passenger didn't survive. 1, passenger did survive. So we can see in cluster 1 there are 215 observations of passengers that didn't survive, and then 137 observations of passengers that did survive. Cool. So after that, we get a output of within cluster MSE per cluster, and then between cluster MSE across all, along with the total within cluster MSE here as well, also along with the sizes of each cluster. There's a cautionary warning provided by the function saying that you need to be careful comparing the MSE of this classification model to the regression models, and that's because regression models predict in a continuous space, whereas the classification models are predicting in a binary or categorical space. So the error calculations is going to end up using different numbers. So a comparison between them, so if we have a look here, even with other classification models, especially with k-means, a comparison is going to be very wrong. So if you were to say that, oh, I'm going to pick this k-means model or this KNN model over the regression models because they had a lower MSE, that wouldn't be the right way to go about it because of how they calculate. So that's why that caution warning is there. But either way, continuing on, we get the MSE. Actually, I'll also add to that, the reason why we then still report MSE is so that you can compare models of the same, so you can compare k-means models to other k-means models made within the function. So if I was to run this again, changing a few settings or predicting a different variable, we can compare the MSEs gotten for each model for each run. And then along with the MSE, we've got a prediction accuracy of predicting exactly. And for k-means, you're not really supposed to use k-means for predictions, but the way that it decides a variable in k-means is it picks the max value within a cluster as the variable it will predict for your dependent variable. So here, cluster 1 is going to predict that the passenger didn't survive, and cluster 2 is going to predict the passenger didn't survive. So at the end of the day, our k-means model is just predicting that all the passengers didn't survive. So very, very dark, very morbid. But either way, we end up with a prediction accuracy of 0.6. Not the best. You can see that it's not really a nice kind of prediction accuracy. And so we can kind of conclude that there isn't really two natural clusters around people that survived and didn't survive. So that's something which we consider and we can learn by doing an initial run of automodel. Cool. So that's k-means. We're now going back into our cleaning steps after that. So we're now going into correlation checks. So in this, how it does correlation checks is it calculates two correlation matrices. It calculates the full one, so it includes the diagonal, the lower triangle and the upper triangle, and then it calculates just the lower triangle. And what it's doing is it's summing the counts of correlation coefficients above a certain level and using that to help decide on what variables should be removed. So it's a bit confusing. I'm going to be hesitant to provide an example because it would take too much time and it's not what's important here. So if you just think about that, kind of see if you can visualize that. But either way, what it's going to do is it's going to look for those variables using that method and remove them if it finds any correlation. In our run, there were no correlated variables found, so 0 variables have been removed. The level which the correlation coefficient is considered like highly correlated can be set by the user. So we'll give an example. So if we go here, core conf level. So by default it's 0.8 or 80% correlation. We can change it to 0.9 to be more lax on the correlation, or we can change it to 0.7 to be more rigorous. So that's there. Cool. Yep, there we are. So that's that there. There is a feature of the correlation where if you saw that a variable got removed that you wanted to keep because of the correlation checks, you can move that variable to the end of your data set, and what will happen is that when it finds that correlation, it's more likely to remove the other variable in that correlation pair than the one that was removed previously. So it gives the user a little bit more of a manual control over what variables are removed at this stage. So after that, it's then going to attempt a train test split. So what it means by attempting is that it's going to try and find a test train split where the training set made maintains variance in all the variables within it. So what that means is that it doesn't want, the training set doesn't want the variables to have all the, like have a variable which just has all the same values for a variable. So it's going to iterate through a loop until it finds a good random split, and once it's found it, it'll say good train test split found, and then that's what it'll use going forward into the models. Cool. So that's the end of the cleaning and transforming stage. There is, after the train test split, the option for the user to do a PCA transformation, or principal component analysis. Similar to the imputation, what you have to do is set PCA flag to true. And what this is going to do is do a principal component analysis on your data set. It will also do a dimensionality reduction if wanted, so you can do PC conf level. So unfortunately can't remember off the top of my mind, so we can just have a quick look at the documentation. So if we do this, boop, here we go, we can look at the variables. PC percent, so we got PC percent. So we can perform dimensionality reduction. By default, it's set to the 95%. 95% of the variance needs to be explained by the principal components. To keep more principal components, we can set to 99. To keep less, we can set to 90. And then that's our way of performing dimensionality reduction in principal components. Cool. So we will go back to where we were. Cool. Oh yeah, I would also say the reason why it's not set to true automatically is that it will, doing principal component analysis transforms your data into a mathematically abstract space where you won't be able to, it's going to be very hard to make any kind of inference from the variables found in like the ordinary linear regression model, the CART model, and or like the variables useful for predicting in those. So by default it's set to false, so you can still get that out as like kind of a summary look at which variables were the most useful. However, it's included as a feature if you wanted to try and just make the best reduced model, if interested. Okay, so enough about PCA. Onto our models. So KNN. This is K nearest neighbors. It's a classification model where, given a test point, it considers the K nearest neighbors to classify that test point. So in this model, we've considered 30 neighbors. This is something that can be set by the user, so if they want to consider more or less, the default is set to the square root of the number of observations in the data set, which is just a kind of rough guess at the best number. So below that, we get a predictions table where along the vertical we get the value that KNN predicted, and then along the horizontal we get the real value that of survived, I should say. So 104 for 104 observations, KNN predicted that the passenger didn't survive, and in reality the passenger didn't survive. 35 times it predicted the passenger didn't survive, in reality the passenger did survive. 7 times passenger didn't survive, for seven observations it predicted the passenger did survive, and in reality they didn't. And then for 31 observations, predicted that the passenger did survive. In reality, they did. From there, we can calculate a MSE. Again, the same caution is given here for comparing the MSE across model. Should be considered more so just for comparing per run. But we get an MSE of 0.0113. And then we get a prediction accuracy, or an exact prediction accuracy, which is 0.76, so 76%. Cool, so that's our KNN. So from there, we're now moving on to our CART prediction model, so our classification and regression tree model. What we get as an output is a summary of the tree and what splits occurred. You can follow along. It may be a bit strange if you've never seen a regression tree before. They're very good to see as a plot. If you're interested in going and exploring them further, it'll fit into your head better. But to follow along, you've got your node, your split, the number of observations, or well, this is the condition it's split on, the number of observations because of the split, the deviance, which is a measure of goodness of fit, and then the y val that node has, or because we're working with a binary variable, it seems a bit strange, but it's basically just what it predicts for y at that node. Cool, so you can go through, you can see we've got our root node here, which is all of our observations, then gone on to our second node, which is decided by the split on the passenger's sex or their gender, on the passenger's sex, which is deciding whether they're male or female, and it could be greater than or equal to 0.5. So this split is if the sex was greater than or equal to 0.5, you would get 331 observations in this split. And then if we go to node 3, it's if it was less than 0.5, which is the rest, which is 199. And then that gives us our first kind of 2 nodes of the tree. And if I remember how it's encoded, 1 means male and 0 meant female. And so if we were to give like a rough understanding of what it's predicted for the y value on each of these nodes, so basically we're saying the node is saying if they were male, they were more likely to have not survived because this value is closer to 0 than 1. And then here it's saying if they were female, they were more likely to have survived because this value is closer to 1 than 0. There we are. And after that, it gives a list of variables that were considered important or the most significant in predicting survived. And so we can see that sex.male is our most important variable according to the CART model. We then go on to the fare, which is how much they paid for the ticket. We then go on to the ticket type, the passenger's class, so the class of the ticket, and for this one exactly, because it's a dummy variable, it's if it was of class 3 or not. We then got age, then sib.sp.1, which is how many siblings they had aboard the Titanic, and so on and so forth from here. From that, we then get an MSE of the prediction on the test values. So we've got a value of 0.1238, and then we get an exact prediction accuracy of 0.82. So there's no caution here because the MSE in the regression models, so this is the CART, ordinary linear regression, and ElasticNet, can be compared since they all use the same space of prediction and the same, equation to calculate the MSE. So here, and then we can also look at the exact accuracy. So this is actually pretty good. It's giving us a correct prediction 82% of the time. So that's CART. Moving on from there, we're now going on to the bread and butter ordinary linear regression. So in our ordinary linear regression, there is a variance or a VIF removal step, so removal by VIF, and then a backward selection step, or just a selection step, based on the variable significance. And then along the way, to evaluate how the steps have changed the model, we look at the AIC, or the Alkine Infinite Criterion. May have butchered that, so apologies. But we look at the AIC to see how the model has improved or made worse via changes. So this is our full model. AIC is 502. The only thing we're interested in with AIC is the differences in the values, not the actual magnitude. The magnitude of AIC doesn't really tell us too much about how it's done. So we've got 502. Then various inflation factor removal. We found 0 variables that had a VIF score higher than 10. Why it's 10 is, again, it's a default, but can be set by the user. I believe it's VIF selection level. Perfect. can be set to 20 if you want to be less rigorous on VIF, or it can be set to 5 if you want to be more. An example of why you would want to change this to something like 20, or one which I've come across myself, is because VIF is based on R squared. R squared is biased against datasets which have a large amount of predictor variables. So when it comes to the VIF selection step, these datasets with a large amount of variables will end up having a lot of their variables removed purely because R squared is biased against them there being so many. So in those cases, saying VIF to a little bit higher, so maybe 15 or 20, will be a little bit more optimal for your data set, and it will end up providing, hopefully, with a better model. So can then go from there. So that's our VIF. So after that, we're now onto our backward selection via the significance of each variable in the model. So our backward selection has removed 13 out of the 19 variables. Keep in mind, even though the original data had 12, the reason why it's now gone up to 19 is because of dommatization. So it said 13 out of 19 aren't significant at the 95% confidence level. Again, another variable that can be changed with model sig level. By default, set to 0.95. Be more vigorous, you can do 0.99. Less rigorous, 0.9. And then you get to see which variables were removed. So we saw the fare was removed, name, passenger ID, ticket, some parch levels, and some sib.sp levels. Cool. And then after all those steps, we now can look at our final improved model via these steps. And we can see that it's considered passenger class of 2 and a passenger class of 3 as significant. The sex of the passenger, the age, and then if they had 3 or 4 siblings aboard the Titanic. And then get our R squared values, so not the best. We get a p-value for the f-test, very significant there. And then we get an AIC and an MSE on the training data. And our AIC here is 496. If we compare it to the full model of 502, we can see that there has been an improvement by doing the selection process, so that's good. So after that, we then have a look at how it does at predicting. So we get an MSE of the predicted values. So this is different from this MSE, as this MSE is calculated using the training data, and this MSE is calculated using the testing data. So that's a thing to remember. And then after that, it gives you an exact prediction accuracy. So the linear model had an exact one of 80%. And then it gives a prediction within a confidence interval, which in the case of survived, which is just a binary variable, it doesn't make too much sense to use a confidence interval. However, if we had a continuous one, this would make more sense. It gives you a little bit more of an insight into how your prediction's done. But yeah, we'll ignore it for this case. Then after that, we go on to our last model, which is the elastic net regression. What this is it's like linear regression, but instead of minimizing the sum of the squared residuals, we're minimizing the sum of the squared residuals plus a penalty or a bias, which is based on the slope of the fitted line. Within that penalty, there's a few tuning parameters which it goes through, and that's what happens in our process here is it tries all these different values of alpha or that tuning parameter in that penalty to see what made the penalty the best fit for the data. But anyway, as we go forward, what we get here is a similar output to the above, where we get a estimate coefficients, so what it would deem significant, so a passenger class of 3, the sex of the passenger, the fare, and then embarked. You can see some differences and also some similarities. So by seeing the similarities between passenger class 3 and sex male, you can see that these variables seem to be quite crucial to predicting the survived variable. So they're worth investigating further for the relationship between. And then after that, we get our prediction accuracy. So we get our MSE of the predicted values, and we get 0.1474. Worth noting, it's a little bit higher than the MSE of the linear one, so not as good of a fit. Then we get an alpha of the tuning used in the equation that you're trying to reduce. Best to say minimizing the sum of the squared residuals plus the penalty. That's the alpha within the penalty, or of the best fit. It tried, so in this run, it's tried the alpha values from 0 to 10, and this can be decided by, if you go into another one, you can do elastic count. So here, it's basically saying try every model in iterations of 1 divided by elastic count. So 1 divided by 10 is 0.1. So it tries alphas in iterations from 0, 0.1, 0.2, 0.3, so on and so forth. Cool. Then from there we get an exact prediction accuracy of 0.81. Cool. And that's our run. At the end we get the time results, which gives us how long this functions take. With this data frame, it hasn't taken that long. Sometimes with much larger ones, it can take quite long, sometimes up to 20 to 30 minutes, depending on what processes you've done. Imputation is especially computationally expensive, so worth considering that with larger data sets. But yeah, that's an example rundown of what the auto model function does. I wish people could go and play around with it if they wanted to. Unfortunately, it's local to my machine, so it will just be here. But yeah, it's been quite fun to make, and it's been nice to go through. Anyway, take care and thanks for watching.